This conference will now be recorded.
Okay, so good evening, Deepa. Today we are going to start a new chapter, that is the ray optics, or it is called ray optics and optical instruments. This is ninth chapter in your textbook, ncert textbook. So mainly in this chapter, we will be learning spherical mirror and spherical etc., and how to form images etc. And you might be having prior knowledge from your previous classes as well, little bit. We'll go a little further detail here. So in this lecture, first we'll introduce what is ray optics, and then we'll see laws of reflection in plane mirror and spherical mirror. What are the sign conventions, etc. We'll learn today, and few terms related to spherical mirror we'll be learning today. So first of all, what is optics? It is actually the branch of physics. Okay, it is a branch of physics which deals with the study of nature, production and propagation of light. Okay, what is the nature of light, production and propagation of light? So if I say light, so what is light? In the previous chapter we have learned something called electromagnetic wave, right? Electromagnetic wave. So in the electromagnetic wave spectrum in the sense, you might be seeing various colors in the visible light. Okay, so light is actually an electromagnetic wave. Okay, light is an electromagnetic wave which has wavelength ranging from 400 nanometer to something like 750, or some book says 800 nanometer. Okay, so this is a part of electromagnetic spectrum. See, in the electromagnetic wave there are radio waves, then you have X-ray, gamma rays, okay, etc. These are having high frequency or high energy and low wavelength. Okay, all this. Obviously radio wave is long wavelength, but among the whole spectrum of the electromagnetic wave, only this range of wavelength is sensitive or visible by our human eyes. Okay, human eyes can sense or detect this range of electromagnetic wave spectrum. Okay, this range of electromagnetic wave, and this is called light. And light is such a like such an important factor that without light nothing can be predictable, nothing can be visible, and without vision there is no interpretation to the world itself. Without vision there is no interpretation to the world itself. We cannot say anything about the world. So we are lucky to have eyes which can detect a nice spectrum of light, like colors. Okay, we have vib right? vib the 7 colors we detect with our eyes, right? So these these 7 colors actually are coming under 400 to 750 nanometer, this wavelength range. Okay, so somewhat you have this idea about vib what all those things: violet, indigo, blue, green, yellow, orange and red, right? So today in the see, in this branch of physics where we discuss about light, its production, its nature, and how it propagates, etc. So this branch of physics is called optics. And in this optics, actually there are another two sub branches. One is called ray optics or geometrical optics, which is the subject matter of this chapter, ray optics and optical instruments. And another branch is called physical optics or wave optics. So from the name itself you can understand ray optics means here light is denoted or interpreted as, okay, denoted by rays. Okay, rays, denoted by rays. So what is ray? Ray is actually like this, an arrowhead. Okay, and in this ray optics we assume that light propagates in straight line. Okay, and the path in which it goes from one point to another, so the path it follows to go from A to B, suppose, this path is called ray. And when you take many rays together, this as a whole is called beam of light. Beam of light. So a bunch of rays together called beam of light. Okay, beam of light. So in the ray optics, what is our main, like what are the concerns, like point of concerns over here? See, ray optics means we assume that light propagates in a rectilinear path. Rectilinear means linear or straight line path. And you know, this rectilinear propagation is actually described by Descartes. Okay, Descartes, scientist Descartes, giving his famous model first, that is corpuscular model, that you can see. Corpuscular means particle model. Corpuscular model or particle model. I'll write about it. Corpuscular model. Actually, this model was later given in a modified and in a, like on the basis of experimental evidences by Newton. First, it was given by corpuscular nature of the light was first talked about this for corpuscular model by Descartes. Later, scientist and the pioneer of many facts of physics, that is Newton. Not only physics, even mathematics, he had great contribution in the science, both in mathematics and physics. Calculus was given by Newton, Sir Isaac Newton, and corpuscular model, and the famous laws of motion given by the whole classical mechanics. Okay, the basic classical mechanics which you read in 11th standard is given by Newton, Sir Isaac Newton. Okay, and he had great influence during his time, and he had taken up the idea of particle or corpuscular model of the light, and he had written a book called Optics. Optics. So in his famous book Optics, he had given the model corpuscular model. What is this model saying? This model is saying that light propagates in a rectilinear path. How could he say this? His assumption was that light may be thought of composed of particles like your classical object. Okay, classical objects are thought of combination of particles or composed of particles, tiny particles having energy. Okay, tiny particles having some energy. Okay, and these tiny particles are actually dimensionally very small, tiny, very tiny, so almost dimensionless or point particle, you can say dimensionless, but they have energy. So these tiny particles, if I think that light is composed of such tiny particles, just by assuming that, like, see, if you just throw a ball or a small particle, if you throw, it will follow a straight path. Okay, it will follow a straight path. If there is obstacle, it will be reflected back. Okay, like this. So if the surface where the light particles are, these corpuscles of light are reflecting, if this is smooth, then it can be shown that there is a reflection. So if you think that the light is composed of such tiny particles having some energy, then the path of the light will be always straight line. Okay, so this is the main fact in ray optics. We'll always take this assumption that light propagates in rectilinear path, and the model or the theory behind is that the corpuscular theory or corpuscular model or the particle model of light that was given by Sir Isaac Newton, and depending on that, we say the light propagates in a straight line. But it is not true. In the nature, we see both kind of phenomena. See, like reflection and refraction, these are phenomena. So reflection or refraction, these are two phenomena which can be explained well by this corpuscular model or ray optics model. And this will be the whole object of our study in this chapter, ray optics. The optical instruments are also made upon the properties of reflection and refraction. Okay, these were very much applicable or very much successful theory when we explain laws of reflection and laws of refraction. But it was very difficult to explain certain phenomena, like, see, so okay, let me tell you, like, see, if I have two lights and combine them, okay, two light and combine them, you can get somewhere brightness, somewhere darkness. Suppose this part is darkness. Then again some alternatingly like this, bright and dark, bright and dark. If you take two lights and add them up, how can you get bright and dark? There is somewhere light, there is no light, light, no light. Like that, somewhere there is light and some places there is no light. How is it possible to get? So this phenomena is called interference of light. Sorry. This phenomena is called interference of light. If you add two lights, you get somewhere no light, somewhere you get lot of light or brightness. So this is called interference of light. So this was not being able to explain. Okay, we will not be able to explain this interference of light by this corpuscular model or this ray concept of light, okay, or particle concept of light. Another few phenomena I can tell you. Suppose there is a sharp edge like this, and if you have a torch, okay, this is opaque. Opaque means it cannot. This is actually not. This is not a transparent medium. Okay. Suppose you have something like this sharp edge. If you have a torch, okay, and you just flow, you just light it from here, you will see. In principle, you should have seen light only this one to be going, but you will see in practical there will be some light in this region. See, this must be the shadow over here, but you will see some light to be entering here also. Some light you will see, there will be light like this, okay, entering here also. So this is called bending of light. So at the surface light bends somewhat, okay. So this bending of light, saying that the light is not traveling in a straight path, it would have gone like this, but the original path becomes like this. So there is a bending of light. That means the rectilinear propagation of light is also not true, or maybe there are some phenomena where you cannot explain this bending of light with this rectilinear propagation. So there are limitations in this corpuscular theory of the light. And then famous scientist Young, okay, so we'll learn this in wave optics. So then the concept of wave comes here, okay, that will eradicate this ambiguity of this phenomena, okay. Okay, so in this corpuscular theory or ray optics, what we are going to learn, we are going to learn how images are formed by mirrors and lenses. Mirrors may be spherical or plane, and lenses are the part of transparent spherical object, okay, part of that we'll discuss. And we'll discuss design and working principle of optical instruments. So these are the objects in this particular chapter, okay. And in the wave optics we'll be able to explain what is interference, diffraction and polarization. These are the phenomena which are being explained, okay. All right, so with this introduction we'll start our lessons today. The first lesson is behavior of light at the interface of two medium. So you can see there are two medium. Here medium 1, suppose M1, and here it is medium 2, medium 2. So the line which is in the middle of these two medium, medium 1 and medium 2, this line is called interface. So you can say this is the interface. This is the interface interface of the two medium. So when a light ray comes and incident at the interface, suppose this is a point O. So this point is called point of point of incidence of light, and this light is called incident ray. You have this idea maybe a little bit from previous classes. So this is called incident ray. So when a light ray comes and incident at the interface, there are three things happens. One is a part of the light goes back to the first medium itself. So this is the ray. Suppose this is, I'll take this is P O, and this is Q suppose, and this is R. Okay. So the OQ ray, which is going back to the first medium, is called reflected ray, and the phenomena what is happening over here is called reflection. This is called reflected ray, and this phenomenon is called reflection of light. And some part of light will be actually transmitting the medium. Okay, it will just go through the second medium, so this ray is called transmitted or refracted ray, and the phenomenon which is involved in this is called refraction of light. Okay, refracted ray, and phenomenon is called refraction. And in this case, the interesting thing is that the light actually gets bent when it goes from one medium to another medium, transmitting from one medium to another medium. Look, if this is small, okay, so this is suppose R, and this is I1, this is I2. Okay, so this I1 and I2, in case of reflection, we will see, will be equal, and this is called angle of refraction. Okay, and these angles are always measured with the perpendicular drop. See, this is the perpendicular. Suppose sorry, NO and N prime. This is the perpendicular at the interface, and angles are always measured with respect to the perpendicular. Okay, like this. In this case, also like this. All right. So so what happens? There are three things I said. One is reflection. The second phenomena is refraction, which I told that it goes from one medium to another medium through it. This is transmission or refraction. And the third one is called absorption. Okay, some light energy will be absorbed. Absorption of light. Okay, so this is called absorption of light, where some of the light will be absorbed by the medium itself. Okay, so there are three things happening when a light just incidents at the interface of two medium 1 and medium 2. One is reflection, another one is refraction, and the third one is called absorption, where the light gets absorbed by the medium itself. Okay, so now we'll go to see the reflection. First we will take up the reflection. Reflection will not only confine our discussion of reflection only in the plane mirror, but we'll go for spherical mirror, and we'll see how images formed. Okay, there are many things to learn over there. So first of all, let us see what are the laws of reflection. So you are familiar with this law. still I'll just repeat it for your recap or recapitulation. So laws of reflection, first one is the angle of incidence is equal to the angle of reflection. See from here, so this is the normal, and see this is the angle of incidence, so this is theta, you can say I, okay, and this is called angle of reflection, which is also the same. If you say R, this I and R will be always same. So this is the first law of reflection, and obviously we have taken the plane mirror over here. You can see this, we have taken the plane mirror, okay, and see the second law, you know, the incident ray, the reflected ray, and the normal at the point of incidence, all will be lying in the same plane, okay, in the same plane. In this case, all are lying in the vertical plane. This is the plane, vertical plane, you can see they are lying on the vertical plane, and this is the plane mirror, okay, plane mirror. All right, I hope you have understood this, okay. Now the interesting thing and the important thing you have to remember is that these laws are applicable for any surface, not only plane. We have taken these laws of reflection for plane mirror over here, but the important point you have to remember that these laws are applicable for any surfaces. You take any curved surface, you take any curved surface like this, it will be applicable, okay. But now in this chapter we are going to discuss spherical mirrors. So the laws of reflection, these laws of reflections will be all applicable in case of spherical surfaces as well, okay. You can take any arbitrary surfaces, so these laws of reflections are fundamental, which will be applicable for any arbitrary reflecting surfaces, okay. All right, now we'll see what is spherical, what is a spherical mirror, and we'll see few important parameters related to the spherical mirror. Okay, so as I said, spherical mirror. So if you take a hollow sphere, kind of a football, hollow sphere, and just take a part of it, okay, just chop off a part of it, so it will be looking like this, kind of this, okay, which is shown over here. You can see this part of a sphere, okay. You can just realize very well, if you take a spoon, a spoon part, like a spoon, okay, so part of a spoon is actually a spherical mirror. You might have done some activities in your previous classes, I think 10th standard. So spoon is a very good example of spherical mirror. So spherical mirror means if you take a hollow sphere and just chop off a part of the sphere, then you get a part of sphere or the spherical surface, you get spherical surface, okay. And something like this, if you just take this hollow sphere and just get the part of this part, okay, this just chop off this part, so this will give you a mirror called concave mirror. If you just polish the outer part like this, you polish the outer part and use the inner part as the mirror, so this will, so use this part as mirror, so this inner part, then it is called a concave mirror. Concave mirror, you look here, this is the concave mirror, okay. Now you take the same sphere and chop off the other part. So this part, okay, this part, and you look here. If you just polish its inner part and use the outer or bulged part, so this part as mirror, then it is called convex mirror. So now this is the part which is acting as mirror. Okay, this part is acting as mirror. So this is called convex mirror. You can see this here. Okay, this is the convex mirror. So if I say in terms of definition, what is a spherical mirror? This is a reflecting surface which forms part of a hollow sphere, which is formed, okay, or which is designed or obtained from a hollow sphere. It is a part of hollow sphere. So spherical mirror is actually a part of a hollow sphere. Okay, hollow sphere. And as you can see, there are two types of mirror. One is concave mirror, another one is convex mirror. So if you take the bulge part as mirror, this part as mirror, okay, you just keep a candle over here. Okay, candle over here. See, okay, just a minute. Candle over here. So light will go and reflects. Okay, light can reflect from here. There are various properties. I am not drawing the complete picture over here. So this part, if you like use as mirror, then it is called convex mirror. And if you use this part as mirror, this part, this part as mirror, and polish this part, in this case the inner part is polished, so then this is called concave and this is called convex mirror. All right, now see, we'll be defining various parameters. Okay, look here, for both the mirrors the parameters are same. See the middle portion, a middle point of the mirror. If I take this as a mirror, so maybe this point, this point is called pole, denoted by P. What is this called? So this is called pole. You look here, it is denoted. So denoted by P. This is called pole. The middle point of the spherical mirror is called the pole. Okay. All right. So any distances will be measuring for the image formation. We have to take this pole as the reference point. Okay. With respect to what, you will be measuring various distances: image distance, object distance, focal length, radius of curvature, etc. We'll learn what is radius of curvature first. Okay, or center of curvature. Center of curvature, look here, the center of the sphere. Okay, center of the sphere, the mirror is like a part of which sphere, the center of that sphere is called actually center of curvature. I'll just repeat that. It is the center of the sphere of which the mirror forms a part. Okay, that means we have taken a part of a hollow sphere as the mirror, and if you denote the center of that sphere is called center of curvature. So center of curvature. So this is called curve part or curvature, curve part or curvature. So center of that sphere, the curvature is a part of which is called the center of curvature. So center of curvature is the center of that sphere. The spherical mirror is part of which is called center of curvature. So in both cases you look the center of curvature. Now it is very easy to know what is radius of curvature. That means the the line joining the pole and the center of curvature, the line joining the pole and center of curvature, in both cases it is PC. This is denoted by capital R. This is called radius of curvature. What is this called? Radius of curvature. Okay, this is called radius of curvature. So in this case this is R, this is R. Okay, radius of curvature. All right, so we have learned what is pole, what is center of curvature, what is radius of curvature. Now we'll learn what is called principal axis of the mirror. So the line joining the pole and center of curvature, if you just extend that on either side, you will get the principal axis. You look here. This is center of curvature, this is pole. If you join them and extend the line on either side, this will be this principal axis. This is called principal axis. Whenever we discuss about image formation, we'll put or keep the base of the object or image on this principal axis as the reference. Suppose I draw a, like I have an object which is near like in front of the concave mirror here. So this will be the base of the object. So this is A and this is B. This is the base of the object on this principal axis. So you have a lot of, like, this has importance. So this principal axis, this is this principal axis. Okay, the line joining the pole and focus, and if you extend that line on either sides, that will give you the principal axis. And the use of the principal axis is that we will use to put our objects, the base of the object or base of the images will be on this principal axis. All right, now we'll learn what is called linear aperture. This is very, very important. Linear aperture, it is very difficult to understand sometimes. Linear aperture, sorry, aperture, yeah, aperture. There will be only single P. Linear aperture. Okay, what is this linear aperture? This is the diameter of the circular boundary of the spherical mirror. It is the diameter. I'll write the definition. It is the diameter of the boundary of spherical mirror, or the curved part, okay, or the spherical mirror itself. Here see, linear aperture is AB. This is the line which is actually diameter of this curvature itself. Okay, so this is the linear aperture here. AB is the linear aperture. If I just add the two ends of this spherical mirror like this, the length we get or the line we get, this is actually linear aperture. Okay, linear aperture of the spherical mirror. Now we'll learn what is angular aperture. We have learned linear aperture. Now if you just connect the two ends of the mirror, like this to the center of curvature, the angle it subtends these two lines at the center of curvature is called the angular aperture. Look here, ACB. Angle ACB is called angular aperture. So the two ends, if you add with a line, two lines, the two ends of the spherical mirror, if you add to the center, the angle you get between these two lines at the center is called angular aperture. These definitions are important. You have to remember. Okay, what is angular aperture? What is the linear aperture? Okay, ACB is the angular aperture. All right. Now we will go to important parameter in the spherical mirror, that is the principal focus. Principal focus. So what is principal focus? You look, if I have this is actually concave mirror. Concave mirror, because the inner part of the mirror I am just using as like inner part of this spherical portion or curvature I am using as mirror, so this is concave mirror. This bulged part or the outer part I am using, so this is convex mirror. So whenever I say what is principal focus, you have to draw these two figures and you have to define the principal focus for both the mirrors. So when a parallel ray, okay, a beam of parallel ray means parallel to the principal axis. See here, this line is actually through the principal axis. So the rays of light or a beam of light parallel to the principal axis, when it gets reflected, and after reflection they meet at a point on the principal axis, at any point on the principal axis. So that particular point on the principal axis is called focus for concave mirror. I'll repeat. A beam of light which is parallel to the principal axis CP, parallel to the principal axis, upon reflection at the concave surface of the spherical mirror, they meet or converge to a point on the principal axis. They all meet at the point on a principal axis, and that particular point is called principal focus, denoted by capital F. So principal focus is denoted by capital F. Center of curvature is denoted by capital C. Pole is denoted by P. So focus is denoted by, principal focus is denoted by capital F, and the length of this line FP or PF, whatever you say, I'll say PF then. So this length is denoted by small f, called focal length. What is this called? Focal length. Okay, this is called focal length. All right. So in case of convex mirror, look what happens when a parallel beam of light or a beam of light parallel to principal axis incident on a convex mirror. After reflection, they appears to be diverging from a point on the principal axis. They appears to diverge. They are not really just going and diverging from here, but they appears to diverge from a point on the principal axis. This point on the principal axis called principal focus, and also here the same notation F, capital F. Okay, capital F. But one thing we will be discussing, like what is the focal length in this case, also PF, denoted by same F. This is called focal length. But by the sign convention, we will see the focal length for convex will be positive. Okay, positive, and focal length by convention, sign convention, focal length for a concave mirror will be negative. That we will see. So as a combination, if you try to write the definition, then you have to combine both the definition. Suppose you have to say, if a beam of light parallel to the principal axis after reflection meets or converges at a point on the principal axis, or appears to meet or appears to diverge from a point on the principal axis, that particular point is called principal focus. So by this way you can combine both the definitions. So in case of concave, they really meet after reflection. The light parallel rays after reflection really meet at a point on the principal axis. But in case of convex mirror, after reflection they are going away, so they don't meet it. They don't meet at F in principal focus. They appears to meet on the principal focus. Sorry, not appears to meet. They appears to diverge. They appears to diverge from this particular point. Okay, this is called principal focus. And the length or the distance from distance between the pole and this principal focus is denoted by small f, and it is called focal length. Okay, all right. Now we'll see the sign convention. Okay, we'll see the sign convention. Okay, one more thing. The plane which is actually passing through a plane perpendicular to or perpendicular to the principal axis and passing through the principal focus is called focal plane. So see, this is a plane perpendicular to the principal axis, and the plane passing through the principal focus is called focal plane. So the plane passing through the principal focus and which is perpendicular to the principal axis is called focal plane. So sometimes images are formed in the focal plane, not in exactly on the principal axis or somewhere. Sometimes images will be formed on the focal plane also. Okay, now one more definition. What are called paraxial rays? Paraxial rays of light. See, I have a mirror, suppose concave mirror. This is the pole. Okay, this is the pole. So the light rays which are parallel to the principal axis and incident very near to the pole, those are called paraxial rays. And sometimes we'll say that the approximation in case of forming image by mirror or lenses, the rays are taken ideally paraxial rays. That means the rays which are which incident very near to the pole. Okay, the parallel rays which are like which incident very near to the pole of the mirror are called paraxial rays. Paraxial rays, these are called paraxial rays. That means you can say the parallel rays which are very near to the principal axis also. You can say parallel rays which are very near to the principal axis. So that those are called paraxial rays. And we will be taking the approximation of paraxial rays. Yeah. Now we'll go to the sign convention. For a spherical mirror, as I said, there are pole, focus, principal axis, and various parameters. Okay. And when we will be discussing about image formation, that time you have to measure various lengths, okay, or various distances, like see object distance, which is denoted by u, small u in general. Then image distance, which is denoted by small v. Focal length, okay, which is denoted by small f. Radius of curvature, these are the distances which will be measured from pole. See, this is the pole, this is the principal axis, okay. From there we have to measure these distances, so this is denoted by capital R, okay. These are the distances we have to measure. And also look, there are certain rules or conventions to take the signs of these distances: object distance, image distance, focal length, radius of curvature. So these have, like, for various cases you have to take either positive or negative. All parameters either you have to take positive and negative. But in which case we will take positive and which cases we will take negative, that depends on the situation. We'll see what are the situations when we can take the distances as positive and when we can take the distances as negative. Look, if I say this is x-axis, and similarly if we just consider the perpendicular drawn to this x-axis through this pole is the y-axis. If I just think like that, then whatever distances you measure along the positive x, that is, so this is, suppose this is the origin, this is positive x-axis and this side is negative x-axis. Similarly, if you just go here, this is negative y-axis and this is positive y-axis. So whatever distances you measure, right hand side of the pole will be positive, whatever distances you measure. And whatever distances you measure on the left hand side from the pole will be negative, okay. In other words, sometimes it is also useful to remember, so you have a parallel rays, so it is said that the distances you measure in the direction of the light propagation or the direction of the propagation of light are positive, and the distances you measure in the opposite direction of the propagation of light will give you negative, okay. Whatever direction you measure, like see here, this will be positive in this way, here the distances will be positive because you have to measure the distances from the pole. So the light ray, suppose it is just going like this, so it has direction of propagation from left to right. So whatever direction you measure from P, from here to here, will be positive, okay. And whatever distances you measure in the opposite side, in the negative, like opposite to the ray of light, propagation of light, okay, that will be negative. So it is very easy to remember this convention, okay. You have to remember this convention, like see, if I just take a concave mirror, it is concave mirror only. Look, whatever distances an object is placed over here, okay, this upside, when I say measure the distance of this or length of this is along the y-axis, positive y-axis direction, so this has to be taken as positive h, okay. Sometime it is denoted by h1. Now light rays are going and just getting incident on the mirror like this, okay. So the distance of this object, this particular object, this is supposed object, from the center, sorry, center no, this is pole, from the pole, whatever distances we measure, in this case you look, this is the object and this is the pole, so I have to go like this, okay. So this distance will be negative. Okay, in fact this distance is actually object distance, suppose. So it is denoted by u, and u will be having negative values, so negative u. Okay, and see the image has formed like here. Suppose the image has formed here, so you have to find out the distance, image distance from the pole. So you are going from pole to left hand side, so this also will give you negative v. Image distance v will be negative in this case. Now look, the height of the object is, see in this case, for the case of image, the height is in the opposite direction, right? This has to be taken as -8. Whatever height may be, you have to take it negative because it is in the negative y direction. Okay, so whatever distances you have to measure from the pole, and if you go pole to left hand side, all the distances will be negative, and all the distances whatever you measure from the pole to the right hand side will be positive. Okay, I hope you have understood this. And in case of, see, we were showing you the focus. In case of concave mirror, what is the focal length, whether it is positive or negative? So f, pf, this will be negative f in case of concave mirror. What about convex mirror? What will be the position, what will be the sign of this focal length? pf, again it is positive here. Okay, positive over here. So in case of convex mirror, the focal length is positive. Okay, positive sign over here, because it is from pole to right hand side. You look here, this is the one. Okay, and look what is the sign of the radius of curvature. So this is the radius of curvature. In case of convex, this is positive. Okay, in case of concave, it is negative. You look from here, this much. Okay, so like that you have to measure the distances, and these distances with proper sign, with proper sign. Okay, so I'll be actually stopping it here up to the sign convention. Next day we will be learning how image formation happens, how we can, we will be learning various more more properties of this convex and concave mirror, and from those properties we'll be discussing the image formation and the nature of the image. Okay, nature of the images, etc. So image formation, next day we'll be learning image formation. Okay, few more things are there, like what are the nature of image, where will be the position of the image, like with the change in, like if you change the position of the object on the principal axis at various position, if you keep the object, the image formation, the nature of the image and the position of the image will be different every time. Okay, so these are very, very interesting. We'll be discussing all those things in the next class. So that will be on Wednesday. So this is all for today. Deepa, if you have any question related to the definitions I have taught you, or the sign convention or whatever, you can ask me now. Do you have any question, Deepa? Any doubt?
No, sir.
Okay, then we'll just stop it here, and next day we'll be learning very interesting things like formation of like images, and we'll see what are the nature of the images and how the image shifts with the object distances. Okay, these are the things we'll be learning, and obviously this is ray optics as well as it is known as geometrical optics. So we'll be actually using various fact of image like geometry, various properties of geometries we will be using while analyzing the image formation, etc. So all right, so bye for today.
Thank you, sir.